You're listening to the FaceTime with Scientists podcast, where we go into the lab or into the field to learn from scientists about their lives, their work, their struggles, and their joy. Let's go. Hello, everyone. Today I'm here with Bella Smith. You are a PhD student studying material science and nanoparticle things, which I'm really excited because that actually is my area. I did study or make nanoparticles and characterize them when I was a long time ago when I was a master's student. So nano stuff is like I get really nerdy about nano things. Yeah, so can you kind of tell us a little bit about yourself and your material science work, and maybe I think you have some stuff to show us today, and yeah.
Yeah. So thank you so much for having me on here. I think this is like a really great channel, and I'm very excited to share my work. So yeah, I'm a PhD student in material science and engineering, and I study magnetic nanoparticles. So there's like different sectors of that area, but I work more in the biomedical side. So I make nanoparticles and I coat them in polymer, which makes them able to go in aqueous media. And then there's people who study like magnetic hyperthermia, which is using these particles for like cell apoptosis, like
Mm.
magnetic heating, or there's a more bioimaging side, which is where I'm at. I have a video that shows what these nanoparticles look like, and kind of like I can go over like how we make them.
Yeah, that'd be
Okay.
amazing.
So this is them when they first come out. You can see that basically it's like a ferrofluid that's strongly attracted to the magnet. And when they're in this state, they're coated in a oily layer called oleic acid. And the reason that we have to do it first like this in the oily layer is because we have to make them in a process known as thermal decomposition. This is a 350 Celsius metal solder bath. And basically, what we do is we do thermal decomposition of iron acetylacetate, which is like a iron organic complex. And then there's multiple different things you can play with here to create like nanoparticles that are spherical or cubic, or maybe you want to like dope them with different elements. These are magnetite, so Fe3O4 iron oxide, and basically the process is that you mix them together and they start to decompose, and then from that point, the nucleation and growth happens, which then you follow up with like an annealing step to actually oxidize the material. And at this point, they come out looking like this in this ferrofluid. But for biological applications, it's not so helpful having them, being oil soluble. So we have to figure out a way to get them to go into the body. And the way we do that is by using a polymer, polyethylene glycol. This is a pretty common biologically
Yeah.
like safe polymer. We have to do like a 3-step modification process to get the polymer to attach to the surface. Because basically you want to have there's like a bunch of different anchoring groups or like ligands that you can do to functionalize the particles. Some people don't even use polymer. Some people use like silica shells or stuff like that.
Right.
Um, but we use one that's like pretty common is use catechol. So we take like literally like dopamine and we nitrate that so that it becomes extra acidic on the OH groups. And then that's actually what binds to that. And what that process looks like is, oh, so first of all, I'll show you this. So this is what the particles look like on the TEM when they come out, still in that oily layer. So
Yeah,
these
so
are about,
for people who don't know, right, like a TM is like you're
oh, yes,
literally looking at with nanoparticles are so small you can't see them with light, right? So it's like you're having to shoot electrons basically. TM is at them or through them, I don't remember. But I think they
yeah,
yeah, go through them.
it's kind of, yeah. So, yeah, sorry, the TEM is such a strange, thing because you can see how like the particles come at like different, shades of gray and there's like these like
Right.
white marks and stuff. That has to do with like the thickness, that the beam tries to like go through, and also if there's particles, like there's like a very, very small grid. And then, yeah, if the particles end up getting on the underneath, then that like affects it. So when you're like
Oh,
focusing it, it's like it's, yeah, it can make all these weird artifacts.
right,
But when you play with the chemical that you mix in that thermal decomposition, that's what actually can change like the shape. So I'm usually interested in just keeping it simple with spherical particles. And the thing is that there's multiple different ways that you can make these particles. Thermal decomposition probably being the like most annoying, but it gets really nice size distribution. So you can see like a lot of these particles are very similar in size, which makes the math and like the computations with them, like the assumptions later, a lot easier. You don't have to assume that like you have difference, like a big size distribution or anything like that.
right. And when you say the thermal decomposition, is that like the process of like having it in this flask and heating it up literally so that you get this like kind of reaction of nucleation, with like of, basically a little piece starting and then it kind of grows into a particle like that. That's kind of what you're talking about in that process.
Yeah, it's like it's decomposing the organic part off of that iron, so then the actual elemental iron like forms these little seeds that then it can like grow off of. And
Gotcha.
actually in the thermal decomp, the way that I've done it is just like mixing the two things together and just like letting them heat. But you can do an inter there's like a it's not a very well known chemical process of how it actually goes from the starting point to the nanoparticle. But there's something in the middle called an iron oleate. And so some people will make that precursor and then drip it in while that flask is like mixing the other stuff. And that way, that's called a Lemaire drip synthesis, and it can create even more monodisperse size distributions than even you see here. But it requires like an extra week of work to kind of prepare
Uh,
that intermediate.
yeah.
So there's a lot of like tunability here with
Right.
that
Yeah, it's so
process.
crazy. I mean, I have some familiarity with this. So I was making silver nanoparticles when I was a master student. So I'm very familiar with that, like under a hood, this like flask that's warming and you're basically adding things at different time points. It's crazy that you're just kind of like cooking and mixing and then all of a sudden like nanoparticles come out. Like it's crazy. I would think, before that, I was thought like, oh, you make particles by, I don't know, chipping away something really small. Like, no, but you're like kind of growing them with these
Well,
reactions.
that is one way. Like you can't. I think there is like there's top down approaches. So
Uh,
like that would be like I guess ball milling or something. I'm not super familiar with
right.
that. But then there's bottom up. So I think you can even do it with like what like lithography. Other people in my group do solvothermal, which is basically you take the precursors, you take them and you actually put them in an oven in a Teflon like sealed chamber. So basically it's like a high pressure synthesis and it's done in water instead of being done in like an oily coating,
Uh,
which is really nice because then they come out and they're ready to go.
right.
Like you don't have to go through that whole functionalization step, but the size distribution like suffers from that
Yeah.
method. So it's kind of
Gotcha.
got pros and cons both ways.
Yeah, that's so interesting. And when you say functionalization, that's like actually putting things on the surface of the particle, right? So you're putting these chemicals or,
Yeah.
polymers on the surface.
Yeah, and I have a pretty cool so I'll just play it from here. I have a cool video
Oh,
of what it actually looks like when the functionalization's on there. So it starts off the polymer is plastics can have like most commercial plastics like this bottle are going to be like millions of molecular weight, so really big like long molecular chains. um the ones I'm working with range from like 2,000 to 20,000 grams per mole, so it's not really a I mean not in the conventional sense when people think
mm,
about like polymer research. They're much smaller. um and basically, there's this kind of like weird mixing thing that happens where the particles are coated in oil. And so they don't want to go into like water like how the peg does. So you have to find an intermediate zone, which I usually use chloroform for that. So what I was showing here is this is the mixture of nanoparticle and chloroform and polymer and chloroform kind of all together. And then what you have to do is you have to separate out only the particles coated with polymer. So you have to exclude the uncoated particles, the particles that got like semi-coated, and then the free polymer. And that process, once you kind of purify it down, it goes from like that dark color to this like more lighter color as you're getting rid of like a lot of those uncoated ones. But from here, there's a really this yeah. So that's what the final product looks like. So you can literally see how they like you take this liquid that looks like it's just a clear, transparent liquid, and then all of a sudden you basically get like you can see. I would think this is so cool. You can actually see the polymer. Like you can see the little flaky, wiggly
Right.
things in there. And so that's kind of what they go from that black thick liquid you saw in the beginning to like yeah, this like kind of weird floating like light brown color.
Maybe to back up, like what yeah, can you talk about the purpose of making these nanoparticles? Or sorry, yeah, what you're making them for? And you talked
Yeah.
about biomedical applications. I know I studied a little bit about, I was in grad school, I was really interested in imaging, and I did end up taking a class in like MRI, and then I think there you use a lot of, right, do you use like magnetic nanoparticles and that kind of thing to like enhance certain areas of the body on images and that kind of thing?
Yeah, yeah. Actually, this is not so much like my direct focus, but I have done a collaboration before with NIST, the National Lab Institute of Standards and Technology in Colorado, with MRI. So we have used these particles for T2, which is the positive weighted MRI. And specifically, we used a technique called low field MRI. So I think like a standard MRI is like ooh, what is it, like 3 Tesla or something?
Yeah,
Um,
I honestly forget, but
it's
I'll
pretty
trust your
it's pretty
judgment on.
strong. It's pretty strong. And I think that if I remember correctly, the low field MRI is like 30 millitesla, so it's way, way less powerful. And so there's like pros and cons to that. The reason they do low field MRI is because it's literally like a rollable cart that you can bring right up to
Oh,
a patient in the bed. Um, and also I think, it might be safe for people who have metal implants because you don't have a
gotcha.
big stray field. Um, but the image that it creates is obviously worse because it has less power in the field.
Right.
So contrast is really important for creating better images in that.
Gotcha.
Um,
So with the lower field MRI, like you said, less powerful MRI, you might need things like these magnetic nanoparticles to enhance the image. So they would go based on what you put on them, maybe they would target a specific tissue or something like that and enhance like literally the contrast of the image, the black and white that you see on the image because, well, for people who don't know, and I'm gonna mess this up, but right, MRI is based on magnetic fields, and so if you have magnetic nanoparticles, they will interact with that field in a certain way.
Yeah, I might butcher this too because I'm like not so I'm not an expert in MRI, but basically there's T1 weighted and T2 weighted relaxation, and basically what MRI measures, it's essentially an NMR, so nuclear magnetic resonance. So it is tuned for the precession of protons on water molecules. So you apply like a B field, which is like a static gradient field, and so then all of the water molecules they want to align with it. And then when you pull, then you do a radio frequency pulse on top of that, and then, so you have all these particles and they're all aligned this way. And then you go and push them this way and then they fall. And that rate of that flux change, that's what creates the image. And then I think the T1 versus T2 is like if they flux this way or flux like this way. Like
Uh,
it's like based on the rotation. Um, and so what nanoparticles do, and like, for example, if you're getting an MRI right now and you were to go and get contrast, a common one for T1 would be gadolinium chelates. So the problem with that is gadolinium is pretty like toxic. It's not that good for you compared to like iron oxide is basically just rust that's oxidized to a magnetic state. So there's a big push to kind of like find alternative contrasts, but they work in like a little bit of a different way. So the nanoparticles have their own little magnetic field that they produce. So basically they help the like water molecules move faster. If you're next to the nanoparticle and it has this field, then they're going to like feel that field plus the pulse and then have a quicker relaxation, which enhances the contrast in the image.
Oh, that's fascinating. Yeah, I mean, I like took a whole class on this and I forgot, but it sounds familiar. But it's I mean, it's so complicated too, but it's really cool that yeah, I mean, I think I've gotten a couple MRIs because I was an athlete and, you know, you're looking for I think they were looking for, small fractures and stuff like that. If with
Yeah,
nanoparticles, would it also be something you ingest or would it be like something you just inject or something?
I think that they inject it intravenously. There is one that is commercially available. It's called Resivist, and it's a really broad district. It's not like the particles I showed you before. It's the same material, but it has a very huge distribution going from like 3 nanometers up to 50 nanometers in diameter, whereas like the one I showed you was like 20 nanometers with a standard deviation of like 1. So very quite narrow. And the thing about Resivist is that it works well in MRI because you're just kind of trying to get nanoparticles near there. The size doesn't matter quite as much. Although the work I did with NIST, we were studying how the polymer coating affected the relaxivity, and we found that there was some effect. I believe it's because the water, like the way that the water diffuses around the particle, is
Mm,
affected by the polymer coating. But we're still kind of like doing more stuff with that to test it.
gotcha. No, that's super cool.
But then there's a another thing. I'm gonna share a paper. This is not my paper. This is from a group in Berkeley. But so the other, let's zoom in here. So the area I work in is it sounds a lot like MRI. It's called MPI, magnetic particle imaging, but the thing is the way it works is completely different. So these are the kinds of images that it creates.
Okay.
What you have here is actually an MRI, that's the grayscale overlaid with MPI. The MPI is the hot spots. So essentially, MPI measures, and I think they might have a good diagram here. It's actually measuring the tracers themselves. So rather than measuring like the water molecules, you're measuring the tracers in an alternating magnetic field, and then that voltage is what is reconstructed to create the image. So you have to do an overlay like with an MRI or a CT because all you're seeing is nanoparticles. You're not going to see the other tissues. But this has a lot of advantages because it's kind of like a PET scan, so positron emission tomography, which measures like ionizing radiation. So I would say that's like a tracer based imaging. So meaning like you're not going to see anything but the tracer itself in the image.
Right, right.
And maybe that's useful for like like seeing blood flow in the brain. You could like see how the particles move around. Maybe you functionalize the particles with like some antibody that binds to a specific thing, and then you want to go see where it moves to. Um, and the thing about this over positron is that this has basically no signal attenuation, meaning that the so light, if you're just shine a light through your finger, it doesn't like go there's a depth where it won't go through. But magnetic fields, they don't really like interact with our body that way, so
Oh,
it can be deep in there and it won't affect the contrast ability. And also this is a very very fast method, so the I think it's the resolution rate is like 100 milliseconds. So it's very very quick at like, which is why it's good for measuring like blood perfusion or something like that.
Gotcha. Okay, that makes sense. Yeah, because I know there's like lots of different nanoparticles for different, well, for all different kinds of like imaging purposes. Um, but yeah, the idea that the reason for creating magnetic ones in particular would be, yeah, like you mentioned, like you can see them quickly, like yeah, through like blood flow, or you can image all the way through the body. Um, whereas like I know I was when I was at WashU as a master's student, was as a PhD student then, there was a lab doing like PET imaging and they were creating nanoparticles that were actually radioactive for like doing PET imaging, which I don't know like why you would choose that over like magnetic particles. Maybe just I mean they were specifically targeting right like cancer imaging.
Hmm.
But I guess it was just like to work with PET imaging, which they had a lot of like high resolution like PET scanners there. So you're kind of
Yeah,
like
and
having
there's like
different
quantum
tools.
dots and there's all kinds
Right,
of like
right,
you're saying silver particles, gold
right.
the gold particles I think show up a lot in PET or sorry, yeah, PET because there's like and sometimes people will take magnetic particles and coat them in gold
Right.
because something like the gold if you shine a light at it it has like an energy that it releases so it can
Yeah,
release heat from that you can release heat from the nanoparticle losing energy in a magnetic field, or you can generate heat from yeah hitting gold with like the right incident of light or something. So then you kind of get both both effects if you do that.
right. Yeah, so cool. I guess is then you could even go from imaging to say like, okay, now we see it. Now you could hit it with light or magnetic field to where like it heats up and maybe releases a drug or maybe then
Yeah.
attacks a tissue cancer or like you could move from imaging to therapy with like the same particle, I guess, which is really
That's
cool.
the main goal with the like MPI type stuff that I work in is like you can see the particles where it would go and then you would apply the right magnetic field. Usually it's high frequency. High frequency is what causes the heating because basically, if you apply like a alternating field like this, the particle wants to go with it, but as you get really really fast, it's going to lag behind and that lag um well, it produces heat two ways. It can produce heat from like energy loss to the system, like literally magnetic energy loss, or physically as it's rotating in the liquid, that heats up the liquid too. So the idea is that yeah, you would get it to like where you need it to, and then it would distribute a drug or maybe like heat up. I think to kill a cell, again, sorry, this is not my like I don't do the heating so
Yeah,
much, but I think you need to be like 42 Celsius so it doesn't have to heat that much.
right.
But the prolonged there's like an amount of time at that temperature. And also, I think that they've seen that sometimes even if you don't hit 42, the cell still dies. And I think it can be something about like maybe the mechanical agitation or something.
Oh,
So yeah, it's there's the combined therapy is a really cool idea.
right. Yeah. That's so cool. How did you get into this? Well, and I did see, so I, stalked your social media a little bit and you had something recently about your journey, which I thought was really cool that you rode horses and you were talking about like you got interested in um something with materials related to like helping their hooves. Yeah, like how did you get
Yeah.
into material science?
Yeah, so I really that's where I had first started was like learning about plastics actually because so I have a horse, his name's Rebel. I've had him for like 10 years. And he has a lot of trouble with his hoofs, so they're very like soft and I grew up in the low country of the US, so it's a lot of like a lot of like water and stuff that causes their feet to get like bacteria, all different problems.
Uh,
So the common, fix is to put shoes on because the horseshoe helps prevent their hoof from chipping. It's kind of like if you have like a gel nail or something, it just gives it a little bit extra strength. But the problem is that a horse's hoof is really masterfully designed to flex um and like absorb pressure and force as they're running, etc. So when you put a metal, they're usually like steel. I guess they
right.
have aluminum ones too, but you put a metal shoe on there, it totally inhibits the hoof's natural ability to move.
Right. Like it's yeah. I mean steel would be yeah, not flexible at all.
And not only like that has like later effects because then, you can imagine they're stepping and then all that force goes into their knee and their joints and stuff. So it's just it's not a perfect solution. And also, sometimes some horses can be sensitive to like the nails going through, like when they have to nail it through, and the nail should never hurt the horse, but it can if their hooves are weak, then it might just crack off and like not hold. So that's another issue. So there are people who make plastic horseshoes and glue on horseshoes. Now, the issue with that is like, if you're gluing something on there, water and moisture can get underneath,
Um,
which can trap like bacteria. But the point is that I was like having all these problems, and the farrier showed me and let me keep a like an extra plastic shoe that he had, and that's when I was probably like 14 then, and that's when I was starting to like, oh, well, like what does it mean that the plastic can like flex, and like what is that force, and like just starting to learn about mechanical components about plastics, and then also like, well, why is this plastic like chemically like this plastic versus another kind, like why, and how does that affect its properties. So yeah, and then that's kind of like you start looking at plastics and then material science shows up, and yeah, I
right.
thought that was a really interesting subject.
Yeah, no, that's so cool. I didn't know that they made plastic shoes for horses, and I was gonna say
It's
like,
pretty new. It's
I was gonna say, and when are we gonna get to the point where like horses have like tennis shoes, basically? Like,
they have that. No, they have
really?
that. So, like, the plastic shoes would be, like, a permanent th like, or not permanent, but, like, every 5 weeks or whatever, but they actually have little, like, running shoe things that you put on just when you're gonna, like, ride or something, and those also have a bunch of, like, material design into, like, the foam on the inside because
Right.
they're very heavy, right? So it would definitely has to be strong enough to not just immediately shear when they step on it, and their hooves are sharp, can be sharp and stuff, but like also be like, yeah, like pressing up on their the underneath of their hoof is called the frog, and that's like a very important area that has good ground contact, which is another thing that metal shoes get rid of because that's the
Uh,
blood flow. So basically it helps push blood through their leg. And so those little tennis shoes, they have to, yeah, produce the force, and be also strong enough to withstand that force.
yeah, it's so cool. I did a deep dive. I was recently doing just a video, or actually, sorry, writing a script for a show for kids to learn about engineering, and we chose like tennis shoes as like, you know, showing what material scientists do, which was really fascinating because like I never knew so much went into creating and designing tennis shoes as when I like deep dove into like, yeah, I mean there's like tons of material science and like really smart technology to like how do you make a shoe, like how do you combine materials like different foams and different things to like some of them, absorb that like sharp impact, some of them just make it comfy, like all the things, right? And so that's yeah, I feel like if I was gonna get into material science, like, that would definitely get me in to be like, "Oh my gosh," so, it's so cool that we can design for different purposes based on, like, combining different types of materials together.
Yeah, I think like textile science and yeah, like the design of like foams, like mattresses, like all that stuff is material science. And I think people, a lot of times there's a lot of research right now going into the more inorganic material side of stuff, so like batteries, ceramics and like metals for
Right.
aerospace. But a lot of people don't realize that, yeah, like everything plastic, all the clothes you wear, like even dye chemistry, almost kind of like there's a lot of stuff that kind of falls a little bit into materials, a little bit into chemistry, but like anything with textiles or like, yeah, designing shoes and stuff, I think that that's really cool. And that's kind of always been something that I've like wanted to explore more when I'm like finished here.
Yeah. No, that's super cool. Yeah.
But so with the like kind of how I got into the nanoparticle area was because yeah, I was interested in like polymers and stuff, and so I knew that this project involved polymers. I never liked E and M like in physics. Electricity and magnetism was not My favorite subject. But when I was a sophomore, there was a program that became available where I was able to work with my advisor was like the one who was heading that program up. And that's yeah, how it got into I was like, well, this is still bio applications, whatever. And yeah, it's like magnetism, but you know, it was like a new experience. And then I just never left. So that's kind of
Yeah.
how I got into that specific area.
That's super cool. Yeah, I think nanoparticles well, and maybe can you talk a little bit about, like yeah, you're working with things you can't see directly. So, I mean, yes, you
Yeah.
can see the liquid, but I think they're fascinating just because, like, a lot of people don't understand the scale of nanoparticles, but I mean, even smaller than like light would be able to see, right?
Mhm.
Like you need to shoot electrons at it to be able to see it. It's like very, very tiny. And it has like special properties because of that. And I guess anything you're putting into the human body that needs to get into a cell or I don't know if these things, like, can cross the blood-brain barrier at all, but you need things that are very small and that, like, yeah, look like something that the body would would normally be in the body, not like some I mean, I guess if you put just, like, pure iron in the body, iron particles, maybe your body would just flush it out, I don't know. Well, maybe it flushes it out anyway, but yeah. How does
Yeah,
that
it's
kinda
the liver these particles get absorbed by the liver a lot. And actually it's a bit of an issue for people who do magnetic particle imaging because if you want to image something near the liver is always just a hot spot because yeah,
Right.
it's totally safe. Like it is just iron. And PEG also has been tested to be, you know, safe. We do collaborations with different cell groups for that. But yeah, the body will just like it is just the liver is a magnet to iron. So we always
Right.
kind of say like, yeah, you know, well, we already know it's not toxic, but also maybe it's a little good for you because you're just getting like a little bit extra iron. Like,
Oh, yeah, true, true. I guess if you're yeah, if you need extra iron, maybe.
yeah.
That's super cool.
But I think, where like, how my project everybody in our group does stuff related to magnetite nanoparticles. Like, we have, people who do calorimetry, so that's more collabed with chemi, but basically, they're producing particles that maximize, heating in a high frequency alternating magnetic field. And the particles that are gonna do well in that are not going to do so good in like MRI imaging. And even MRI imaging particles are completely different than MPI imaging particles. Because like even though they're very similar, the physics is different. So you have to like tailor the particles for each specific application. And the things you can tailor would be like the size, you know, if you dope different metals in there, like sometimes we'll put cobalt or manganese or zinc, and that affects the overall magnetic performance. The shape. One of my lab mates does like she makes magnetic rods, magnetic
Oh,
cylinders, like tubes, like all kinds of weird shapes. And that has like effects for like magnetic hyperthermia, which is that like yeah, that's set the heating for drug delivery, etc. So yeah, there's kind of like a lot of different avenues. I got into the imaging space because actually I'll show a video of this. So my advisor wanted me to make a what's called a magnetic particle spectrometer. So okay, here it is. Um So this device is something that I built. And now I did not design this. This is an um, open source MPS on GitHub. And the guy who designed it was out of MIT, and he helped me a ton because I only ever
oh,
took one electrical engineering class like in undergrad. I didn't know anything about soldering or electrical filters or anything like that. I just kind of figured it out and, you know, used the resources available to me.
that's amazing.
But basically, I'll kind of step through like what it is. So basically, you have this, and this is all like 3D printed and hand wound and all this stuff.
Wow.
But Basically, you have this like two magnetic drive coils. So you have like a big one here, and then there is a smaller one that I show. Sorry, I show it later here. Um, yeah, so that here, this one. There's two drive coils, and then this guy that sits inside this coil here, this is the receive coil. So basically, you drive a magnetic field with the two big ones. The reason there's two is because we do different frequencies. So you can do like one at like 20 kilohertz and then one at like 20 hertz. So very different frequencies, and you can do them at the same time and pulse them and whatnot to kind of see different relaxation effects. And then that coil here, that's called a gradiometric coil. So basically, the two bigger sections of wire, those are counterwound. So the nanoparticles sit in this top one. So the sample goes in, the magnetic field is applied, and then the signal that they produce, it induces a voltage into that coil. That's like the Faraday's law of induction. And then on the bottom, this other coil, the reason it's counterwound is because basically the particles feel the field you apply, and then they also produce a field, right? So that top coil sees both. The bottom coil only sees the field you apply. And so then you're able to subtract those two. So that way you only get
Uh,
the signal of the particle. Um, and to produce that, like all of this stuff in the background, this is like a band pass filter. So this is like a electrical filter that makes it so that the frequency you're sending is exactly the one you want. This is, yeah, so this is kind of how it sits inside, and the nanoparticle goes here. And so then, yeah, you can kind of see how it kind of goes in like that. Um, and what's happening inside the coil, the x-axis here is basically the magnetic field that you're applying. So it's alternating between, up and down. It's a sine wave. And the particles want to, at some moment, the field is positive, it's all up, and sometimes it's down. And the particles want to, you can imagine they have like a little dipole. Every little iron atom has its own moment, but you take like the sum of the moments and you can just represent it as like an arrow. And so you can imagine when the field is up, the particles want to all be up and vice versa. But it takes time. And, when you have no field applied, just like they're sitting on the bench, they're all in a random distribution. So then
gotcha.
there's like some lag to get there. And then since you're switching it so quickly, that's kind of what's happening. And that's what causes that induced voltage is the flux as they're going from random to aligned and back again. So this is kind of the actual like computer software. This is like through LabVIEW. So this is like actually like what the measurements look like when it's being run. So this creates something called this top left graph with the black and white here is called the point spread function. This is for people who do MPI. So they are interested in the full width half max, which is basically you take half of the intensity of this like one curve here, and then like what's the width there. And that plugs back into an equation about that like basically correlates to the resolution. So how detailed of an image can you actually get? So we're trying to make particles kind of being in between instrumentation and synthesis. That's kind of like where I sit. I try to make particles that have optimal performance for MPI.
Gotcha.
And
Yeah,
that
that's what I was gonna ask. Like, so is this telling you something about the size of the particles, the some type of property of their magnetism? Like what would make, yeah, like why do you have to use this spectrometer to like measure these things? And then like how would you tune that?
my main area of focus has been polymer coating. And so the idea is that if you have a really big polymer coating, then the nanoparticles are basically isolated. They are not interacting with each other at all. And if you have a small coating, they can aggregate in solution and they have a dipolar interaction with each other. And the thing about that is that it can be either a beneficial effect where like they would magnetize quicker
Oh,
like than they ordinarily would, or it can be detrimental because they might be wanting to go up and the other one, says no, you're going to go down. And so and it's kind of random. Like, it's a very random effect, and, like, because every time that they aggregate in a different way. And these aggregates are not, like, something that you can see, like,
Right.
I'm talking about, like, 3 nanoparticles clumping together.
Oh,
Um, Actually, I'm gonna go back for a second to that other paper that I had, because they have a diagram, I think, that, like, literally shows what I'm talking about. So, yeah, so these
right.
people okay, so see first look at this E, the black here. This is what I mean by talking about, like, the resolution enhancement, of, like, how much more detailed you can see when a particle is actually designed for MPI. These
Oh,
are MPI images. And now what they were kind of doing is they've got these particles in these clusters that all align. And so then there's like a very beneficial thing. You can imagine if the particles were in a chain, they will, yeah, help each other out because they're all like aligning in the same direction. But if they were in a clump, then that might not be the case because they might all subtract from each other. And I think they have an image. Yeah. So yeah, so see how the particles can form these clumps.
oh,
Now these are pretty big. I mean, this is like a
right.
micrometer. So that's kind of bigger than the aggregates I've been seeing. I had to do something called small angle X-ray scattering to see that I had aggregates because literally mine are only like 2 or 3 particles coming together. I'm not getting these big like clumps like this. But the MPS okay, this graph is here. This here. So this is like that same kind of graph I was showing um
Right, of like the
with the
S's.
with the
Yeah,
dipoles. Yeah.
yeah.
And so here you can see how different particles or well this is different instruments, but you can just imagine for a second these are different particles each color. So the black curve would be like the optimal um MPS or MPI, performance because it's very, very sharp. So basically that means you turn the field on and the particles instantly they're there. You don't want
Gotcha.
them to lag because there's no information in the lag. There's information in them turning on and turning off. Um, so basically things like particle size, dopants, clustering, um, the shape, those all affect the sharpness of that magnetization curve. And like you can look at that with this plot, or you can look at it as those derivative plots, which were the 2 humps, that point spread function thing. You can use that to back calculate to like size, viscosity, like yeah, like understanding those things. I think the way that it's most commonly used would be not necessarily like, oh, we're gonna figure out that the viscosity is exactly this value. Because it's not so absolute like that. It's more like, okay, I have a nanoparticle that has an antibody attachment to it. And then I have an antibody, and if it binds, that completely changes how the particle will relax. It'll become really slow because you're going now it's really big.
Right.
Um, and you will see that change. So people use the MPS for like COVID detection, any, biomarker detection in general, because you'll see a huge magnetic shift there. And the MPS is a
Oh,
very fast instrument for detecting that.
gotcha. That makes sense. So you're literally tuning with coatings on the particles, with different things, you're tuning, like, how much they can clump or that kinda thing in order to see and then you're using the spectrometer to see, okay, like, what will the signal look like for those, and then you can, yeah, meet the requirements of different imaging applications, I guess, from there.
Yeah, exactly. So
Which I
let
think this
me
is the cool thing with right, with engineering in particular, like biomedical engineering. I always struggled because I am a biomedical engineer. I'd be like, why wasn't I just a biologist? Like, what is the engineering part of biomedical
Mhm.
engineering, right? But it is this like thinking about what is the application and strategically be like, okay, we need to design something for that application, like for a specific imaging thing. And so, I mean, I think in biology, you're kind of like asking questions and looking for mechanisms and looking for like, how to antibody or how an antibody binds to a receptor of a cell. But you bring in an engineer to be like, okay, let's think about the problem and how do we design a solution to that problem.
Yeah, exactly. Like I was working with we collaborate a lot with BioE, and I was working on writing an NIH grant with a someone from BioE, and they run our university's COVID lab. So they do like PCR, I think is the main test they do. But we were talking about like looking into testing rabies titers with MPS because there's only one lab in the US that does rabies titers testing. And they have because there's only one, they have a backlog of about a year. So, the reason
Really?
you would want to get your rabies titers, if you ever get bit by an animal that might have rabies, you get the rabies shot just because it's such a dangerous disease. But if you're like somebody who works with animals and you didn't get bitten, but like they just kind of get like their rabies shots done like at a certain frequency, but maybe they don't need it at that frequency. If they had their titers, they would know when they need a booster or
Oh,
not, rather than just getting one all the time.
gotcha.
Um, so it's kind of like, yeah, there's like needs that get met because of that. Also, I think that I don't know much about PCR or like ELISA, but I think that there's like a really long processing that has to happen and it requires really expensive equipment.
Right.
There are now MPS. There's like a group in Minnesota that made an MPS that's like this big. So it's like a portable, yeah, spectrometer that in the nanoparticles, they are really difficult to make, but once you make them, like they're, you don't need much to do these tests.
Gotcha. And with the nanoparticles, somehow they're detecting. Well, I guess your rabies titer is like how much. I don't actually know what it is. Is it like how much of a antibody you still have around for
Yeah,
rabies?
I think so. I think the idea is that the particle would bind to it, and then
Uh,
if there was enough binding, then you would see a signal
You
shift
would
and you
see
would
it really
know.
clearly through like you just have to switch on a switch basically and see like, okay, this is how much we have there based on the attachment of the nanoparticles to it.
Yeah,
Yeah,
pretty much. Yeah.
yeah. That's super cool. Yeah,
And
with the PCR and that kind of stuff, you're like amplifying, you're having to like do a process to, yeah, a whole process to look at specific DNA or, to like, yeah, and I think ELISA is also like some dye basically that would like attach, and then you have to, there's probably just like processing you have to do that's just not as quick to be able to like
mhm.
see that signal turn on and off.
Yeah, and so like the main thing with MPS is you can just use it as straight up like maybe you want to know if there is something attached. Maybe like my lab mate wants to know are these rods or these cubes, and they'll have a different magnetic response. And you can
Oh,
know that immediately by looking at kind of the fingerprint that it produces. Are there particles or they're not particles? Because there just wouldn't be signal, right? If there wasn't, that's part of the cell tracking or particle tracking. But then also, if the particle was like in blood and then it got absorbed by a cell, the viscosity would be very different in that situation, and so the magnetic response, it would be a lot slower. And again, you would see that as a different. So then there's something called color MPI, where basically they take, okay, if it's like this rate of yeah, like signal change, we're gonna like assign it to this color. And so again, I could simulate that myself by like running samples in like glycerol or like immobilized or in water, and like how does their signal change, because you would see that too, like, oh, did it get uptake, was the particle absorbed by a cell or not, and you would
oh,
see that
that's
in the
super
image.
cool. So yeah, without using a microscope, without or you wouldn't be able to use a microscope, scanning electron microscope,
Mhm.
without having to use that, you could see just from the signal, like, did it get inside of a cell or not? Which that's
Mhm.
amazing. That's crazy. Yeah, because I mean, I'm guessing to be able to get an image of something like this in a electron microscope, you would have to like, yeah, you would have to take a sample out of the body, make it really thin, right? Put it in the microscope. Like that's very different from like we can just see with the magnetic signal what like
Mhm.
where the particles are.
Yeah, yeah, exactly. And then like also, and people do that. If you're putting it, people who do animal studies, they do like end up, yeah, I guess they do the Prussian staining or whatever and look at the tissues.
Right.
But the other issue with TEM is that, the sample's dried at that point. So
Right.
it's also hard because you don't know if that's actually what the sample looked like when it was in media,
Um,
which is where I've been kind of interested in the X-ray, the Sachs scattering, because again, it doesn't give you an image, but you get an idea of if your particles are isolated or clumping together. And so it gives you just, yeah, a little bit. It's so weird because it's such a in some sense it's such a like a simple concept. Like it's something you learn in like your first year of E&M. Like you have a coil and it can induce signal into another coil via flux. That's all we're doing. Like it really is quite simple in that way, but there's so much like stuff that complicates it. Like, yeah, if the particles clumped, if the humidity changed when I was making the reaction, like sonicating the samples is a huge factor because it controls the clump, the temperature of the particles, like, so it's I kind of like that it's like such a simple idea, but yet there's so much to know about it to like
yeah.
actually understand it.
Yeah. Well, that's a good segue. I was just gonna ask, like, as we wrap up a little bit, because we could talk about nanoparticles all day, but yeah, what's like I don't know, a challenge for you at the moment in your field or life as a scientist, and then how are you overcoming that? And then also maybe, late after that is like what's something you're excited about?
Yeah. So, and this actually like really hits home for me because this has been a major problem for me. Is the data that comes out of this system can be extremely variable, and I have been racking my brain over this for years. Like, oh, is it because I hand wound those coils? Like, is it my fault? Or is it the nanoparticles? Is it like some weird like quantum physics stuff going on where they just like decide to be different every day? And I've been going through tests to try and isolate sources of variability. And I've basically come to the conclusion that it's not the instrument. And like, I know what variability could be coming from the instrument. It's like much smaller than what we're seeing. And I've also done tests on nanoparticles and seen like, oh, yeah, this is causing like variability here. And so the problem is, I've been struggling to like feel like I can really make a claim about anything because the data is variable and I don't know what's causing that variability. So you know what I mean? Like I think it's really important to be honest in science, and I don't
Right.
want to come out and be like, "Oh, yeah, I did this and it affected that," when I'm not sure. I don't know if that's what happened. So one thing I did, and this has really changed kind of my viewpoint on science and finally got me a paper because I was like, I'm never going to get a paper with this thing. Um, I started working with a statistician, and that was 2 years ago. And I went in there and, in science a lot, like we'll make like I can't reproduce these exact particles. I can make like this if I make a batch of them, that's that batch. The next batch will be different. Like they're
Right.
never the same. It's like so he's like, "Oh my gosh." He's like, "You can't really like replicate this stuff." I'm like, I mean, that's just yeah, nobody really replicates stuff in that way because you can't.
Right.
But what I can do with MPS is I can take a lot of measurements. So before I would go and I would make one little tube of something and I would measure it one time. I'd be like, okay, this is my data. Like I want to make some comparisons about like different things that I did to it. Like, can we talk about that? And he's like, you need to measure it more than once. I'm like, really? I was like, if I do XRD, I do XRD once. Everybody does that. Nobody like takes their sample and makes multiple XRDs, right? Or so like you don't like that's just not like it was so foreign to me that that's something that I would need to do. So I listened to him and I did it. And that's when I realized like how big I didn't know that I had variability. I knew that sometimes I would come back and I'd measure the something again, like another day, and it would be different. And I'm like, that's weird. Like, what
Uh,
happened? But
yeah.
then when I actually opened the hood and stopped taking the average of everything, which is like kind of the thing that people do in my field, I was like, oh, like this is like really crazy. This data is really crazy. So basically the takeaway is that there's like a lot of variability that I think people are don't know about because you wouldn't know unless you looked for it, or they just aren't talking about it and are publishing it anyways. And so I really kind of rewrote my whole PhD work because now I work with a statistician. We have a paper on like how do you actually honestly represent data that looks like this using statistical models. Now we're talking about how to use machine learning to classify those samples and like what's the best way to measure them, like how many times do you need to measure them to actually be like certain of what you're
Right.
getting. And then also then using that to then actually have a material science discussion of like, hey, I did this stuff with these polymers. What's the what can I accurately say without overstepping? I don't want to like make a claim that I don't know for a certain is true. And I'm using statistics to like be like really certain that I'm, that's what I'm doing.
That's super cool. Was that, like, just something that you took on yourself? Like, yeah, it sounds like it's not necessarily standard in the field, um, but I'm sure it helps. Yeah, we talk about replication crisis in science, right? Of, like, publishing things, but what's the value of that if you don't know for sure that that someone else will get that same result, right? Um, yeah, it seems really, really cool that you're taking the initiative to, like, do all of these replications, like, measure multiple times and use statistics to be sure of what you're seeing.
Yeah, I felt like I have to, because if I don't, like I don't know what's going on. If I Sometimes I would have a series of samples and it'd be like this sample's here and this sample's here. And then I'd come back the next day and it'd be like this. I'm like, what? Until I was like, I literally will not be able. I've made cool particles. I've done other characterization on them. I know they're good. I know my instrument is like good. So I'm like, why can't I get but like I was just having trouble. And I think it's just the nature when you're doing like dynamic magnetic stuff in fluids. Like we talked about, there's a bunch of variables. And um I think it's real. The data is real, right? Like the variability is actually not something to run away from, but to embrace. And the statistician, like working with him, really helped me realize that. And so it was kind of a, yeah, by mistake that I got into that. Cause I
Yeah,
also don't know any statistics. Like I took like one statistics class in undergrad.
yeah. No, that's super cool. I mean, do you have any idea of where the variability is coming from? Like,
I
I
have
mean,
seen, so there's a commercial particle that I use sometimes. There's other issues. There's no standard.
mm,
Because the problem is the standard, what you're measuring is a nonlinear effect. So you can't really put like like what you would put in something like a vibrating sample magnetometer. You can't really calibrate that the same way that you would calibrate this. So really there is no calibration. The calibration is you put a coil of known wire into it. So we've done that, but that's not really like, yeah, you can't really calibrate the higher harmonics because you only get those if you put a nanoparticle in there. Um, so yeah, sorry, I'm sorry.
yeah,
I
yeah.
lost
No,
my train
yeah,
of
yeah.
thought.
I mean, just like, I mean, I'm sure the variability is coming from lots
Oh
of
yeah, so
different variables that you don't
temperature,
necessarily. Gotcha.
the aggregation states like sonicating. If you don't sonicate a sample, if you do, changes it. Oxidation maybe, like, I mean, there's material things that I would be a pain in the butt to figure out.
Right.
But like these are just guesses.
Right, but like
However,
you
you're
said,
not
like
gonna
if
oxidize
you leave
data.
a sample on the table and you come back the next day and measure it, like, yeah, what's different? I'm sure that particles start to maybe come together or like you said, oxidize or they're they're not a static thing that just stays the same in that
Right.
tube like from day to day.
Yeah, and so I honestly like, especially with the disease detection stuff, when I realized that it was like that, I was like, how are people honestly like doing disease detection with this? Because you don't want to give someone a false positive or false negative. Like that's really important that that doesn't happen. So, but here's the thing: there is variability, but if the let's say the thing that you're testing it against is so different, then
Right.
it won't matter. Because like, yeah, it could
Right.
be like jumping like this, but if this is all the way up here, then it's fine. So I think that's
Right.
kind of how the disease detection has been going along. But we want to improve that, right? Because then what if I want to test something that's like this close together? Well, now if I
Right.
have variability like that, I'm not going to know that. So I'm trying to figure out a way. I don't think you can eliminate the variability, but maybe we can use statistical models and look at like higher dimensions of the data. Like a lot of people only look at one or I talked about how there's like this Fourier transform thing. And so people from that, there's like different harmonics, they're odd multiples of the first one. So people usually look at the third harmonic or the fifth harmonic, and that's it. And that's just like how they will like talk about, oh, the sample versus this sample. Well, we look at like all of them and we put them into this like big principal component analysis type of matrix. And with that, you can get more data. It helps you be like more sensitive when there's variability. So
Right.
hopefully you could like the idea is that you could maybe get higher sensitivity for disease testing if you could, you know how to deal with that variability, because you're not going to get rid of it. You might be able to slightly get rid of it, but you won't fully get rid of it, I don't think.
Right. You just say, yeah, more like account for it. That's
Hmm.
super cool. Yeah, and is there something you're like really excited about? I mean, it seems like you love this. You talk about it with a lot of enthusiasm. Are you hoping to stay in the field after your PhD, like in academia or industry? Like, yeah, what are you looking forward to in terms of nanoparticle
Um,
material science?
yeah, well, so I think the thing that I've gotten like really passionate about is like scientific communication. I I I do love this space, and I've been working in it now for almost 6 years. But I'm looking to go to industry. I'm like kind of looking to stay in the polymer side of things. So I might like completely, I mean, we'll see. Maybe I'll change my mind. But I am looking at industry right now. And I need to stay local to where I live because my husband is a assistant professor at my university.
Nice.
So that's kind of the academia route probably wouldn't like work really
Yeah.
well
Yeah.
with that, but that's fine because
Yeah.
I do have kind of a, yeah, I'm interested in, like, entrepreneurship, I'm interested in, like, industry and collaborating with people, like, I love just, like, learning about what other people are doing and then seeing connections. So, I don't know what job that is, but, that's kinda what I'm looking forward to, and yeah, doing, like, scientific communication for everybody, like, okay, I can talk about nanoparticles, and I know I'm so bad for, like, not explaining things the way that I should, like, forgetting that I've said something and I didn't explain, like, what that meant. But when it
But no,
comes
I
to,
mean,
like,
everybody is, right? Like, it's like that curse of knowledge. Like, it's hard to imagine before we had the knowledge, you know? I mean, I'm the same way. Like, in this stuff, it's like if I know it, then you can just immediately jump to knowing what the acronyms are or like, build upon the knowledge and forgetting like that the base, some people might be like below the base you're assuming.
right, and so I don't wanna be, like, that way because I know what it was like to start, and so I really wanna try to be conscious of, like, when I'm doing that and then, like, stop. But one thing that's been helping with that, and what I think is interesting, going back to, like, the horseshoe thing, that's just a general product, you know, people, like, yeah, especially in the horse world, know about. I'm interested in kind of like showing people how there's material science in everyday products like your nail polish, your
Yeah.
hair, like your shampoo, your conditioner, like things like that. And not only maybe it'll get more people to want to be material scientists, but also just helping like educate consumers about what they're using and like also showing how cool materials can be like yeah, so stuff like that that's what I'm really passionate about right now because I love creating
Yeah,
stuff.
no, that sounds amazing. Yeah, I mean, you're also a model as well, right? Like you do some.
Yeah, I used to be, yeah, yeah, and
Okay.
so that's kinda like I chose I that path kind of, I coulda gone that path or I could have done the engineering path, and so I kinda stayed in engineering, but, I love fashion and I love, like, I don't know, I like making videos and doing stuff like that, so
But
now
like
I'm kind of
combining
trying
those
to
two would be super cool. Yeah.
yeah, so I'm kinda just trying to, like, make my own version of that now, but, like, incorporate materials with it.
Yeah, that's super neat. Amazing. Well, thank you so much for,
Oh, yeah,
yeah,
thank
I've
you.
learned so
Yeah, this was really
much.
fun.
Yeah, sweet. Thank you so much for talking about all of your nanoparticle material science work.
Yeah, no, thanks for having me, it was great.